Bonjour, bienvenue à la séance pour le Prix Pierre-Robillard. I will start by saying that we did find an Apple Pencil from this morning, probably. So I'm going to bring it down at the table in case somebody complains about having lost it. So we're here for the Pierre Robillard 2024 award. It is awarded annually by the SSC to recognize the best thesis in probability or statistics defended at a Canadian university during the previous year. And our winner this year is Qiuqi Wang from the University of Waterloo. It was a thesis written under the supervision of Rudu Wang. The title is Characterizing, Optimizing, and Backtesting Metrics of Risk. It's the first time that the winner comes from actuarial science. And so we're quite thrilled. I'm particularly quite thrilled, given the fact that I was the one who suggested that we should have an actuarial science section in the SSC. His work is in actuarial science and risk management. His thesis shows a lot of breadth, with papers in 4 different fields: actuarial science, mathematical finance, optimization, and management. All of them containing strong probabilistic and statistical components. Practical questions in mathematical finance, including insurance, motivate most of the mathematical developments in the thesis, which in turn inform the risk measures used in practice. Qiuqi is an assistant professor at the Morris R. Greenberg School of Risk Science of Georgia State University. He obtained a BS in Mathematics and Economics in 2017, an MPhil in Mathematics in 2019, both of them at the Hong Kong University of Science and Technology, before completing his PhD in actuarial science at the University of Waterloo. He is also an associate of the Society of Actuaries. He will not be presenting his thesis per se, but rather work related to his thesis. The title is Standard and Comparative e-backtest based on elicitability. And so join me in congratulating him again, even though, of course, he will have to work hard to get our applause again at the end. Thank you.
Okay, thank you so much for the very nice introduction and very nice pronunciation of my name. It's quite hard to pronounce. And thank you so much for coming, because I know that it is the last day of the conference. And again, thank you so much for coming and your recognition. And before we start, I just want to say that we actually have a very nice translation in French for all my slides. And this is done by Thierry, and within a very short period of time, so like 2 or 3 days. And I really appreciate the effort. But unfortunately, due to technical limitation, we cannot show both. But I really want to express my gratitude to all the translation team. And so again, as a brief introduction of myself, my name is Qiuqi Wang, and I graduated from the University of Waterloo in actuarial science. And my supervisor is Professor Rudu Wang, who is here. And now I'm an assistant professor at Georgia State University. So also, I want to thank all the committee members of SSC for the recognition, because I know it's quite special for actuarial science people to receive the Pierre Robillard Award. So really appreciate this, and as a member from the actuarial science committee, I feel very proud and honored to receive the award. And also, after this talk, I hope that we can have a better idea. So actually, the two disciplines of actuarial science and statistics are well connected together. So they are, and you can also see my topic is on actually about statistics. So this is a standard and comparative e-backtest based on elicitability. So as a brief agenda, first I'm going to talk about the backgrounds on risk forecast and also the backtesting approaches to evaluate the risk forecast that we get from the financial institutions. And also the elicitability concept, which is very closely related to the backtesting and forecasting approaches, and should be very familiar to you as the statistics experts. And then I will talk about e-values, which is the brand new notion that we use as a tool to design the model-free standard and comparative backtesting approaches. And I will talk about standard and comparative backtests, model-free ones, separately, because these two are actually two separate problems. And finally, I will talk about simulation study, because this is still an ongoing work. So I only demonstrate a simulation that as a simple illustration of the theoretical frameworks. And I'm going to mention two papers. The first paper is within my PhD thesis on e-backtesting, and this is with my PhD supervisor, Professor Qiuqi Wang, and also Professor Johanna Ziegel from ETH. And but today, mostly I will talk about the second one. So most of the materials in this presentation is about the second paper, which is an extension of this previous work. And this is about this is also a working paper, and we are still in progress. But most of the theoretical results are ready to present. Now this is currently myself, but later I will involve some of my classmates to help me finishing it. Okay, so again, this is one of the first independent projects with, after my graduation, so maybe something is not so mature, and your suggestions and comments will be welcomed. So we start from the two very simple risk measures. And I'm studying quantitative risk management, and I'm dealing with risk measures. So they are basically defined as the mapping from the space of random variables or distributions to real numbers. And here are two most common risk measures that are very familiar to us, the VAR and ES. The VAR is value at risk, and here we distinguish between the lower and upper value at risk. So the lower one is the left quantile of a random variable. And similarly, we can also define the upper value at risk as the right quantile, which is defined very similarly. So we just show one of them. And then we can define expected shortfall. This is the average of the value at risk at the tail part of a random variable. And expected shortfall, ES, can also be called T-var, C-var, or A-var, depending on different situations that we are talking about. Okay, so again, a risk measure is defined, here in our paper, is defined as a mapping from the space of random variables or distributions to real numbers. But here, actually, we have a more, so we generalize this slightly. So we can map to real numbers, but also can map to a space of real numbers, like an interval. Okay. And then we calculate risk measures in practice, but the problem is, in some cases, we don't know the true distributions of the random variables. So in this case, the best we can do is to find the forecast of the risk measures. So here, in a static setup, say you can provide with a point forecast of the risk measure, which is actually unknown, but you forecast it using the forecasting method. And then you find the realized loss. So this is the information that you observe. Then your question is how you can evaluate this. So how you can tell whether this A you provided is good or bad. So a simple approach is that you can define a scoring function and you plug all the information into the scoring function. And then you find a score, a real number. And this is actually the performance. This measures the performance of the forecast that you have. And using this approach, you can compare different forecasts. Say you have forecast 1 and 2, and then you want to compare which one is better. Then you just calculate the scores for both. And the smaller the score, the smaller the loss, and the better the forecast. So very naturally, you can consider if you choose the best forecast, say, in other words, you choose the true value of the risk measure, then it minimizes the score. And in this case, say, if a risk measure, the true risk measure is a minimizer of the expected score for some scoring functions, then we call this functional to be elicitable. Right? So, so this is exactly from the evaluation of risk forecast. And this is quite related to evaluation of risk forecast, and later we'll talk about backtesting. And this is the core concept in backtesting problems. And similarly, we can also define the so-called identifiability. This is quite close. So these two concepts are quite close. And naturally, so to consider their relations is that if you want to find the minimizer of the expected score, then very naturally, sometimes you can calculate the derivatives, right? And set it to be 0 and find a solution. And then if you can find such a solution, and usually this is the minimizer, if you can find it, then say the A is the exact risk measure, and then equivalently you have this is the expected identification function is equal to 0. Then you can see we call this functional to be identifiable. So both concepts are actually related. Here we have some examples, so, very common examples in practice. And first one is, the simplest one is the mean. So actually this is the arc mean of the expected quadratic difference between the loss and the forecast. And we all know this. And secondly, the value at risk is also elicitable with the following scoring function. But here we make some modifications. So we consider an interval between the left quantile and the right quantile. And this interval is the minimizer of the following expected score. And later, we can also change this first dimension, this one-dimensional case to the second dimensional. So we raise it to the power of 2 and find the minimizer of the expected given quadratic score. But we distinguish between the positive and negative parts. Then this is the expectile. And all these three examples are actually single-dimensional. But elicitability can also describe the multi-dimensional risk measures. Say we have a two-dimensional risk measure that is elicitable, then one of them is called co-elicitable with another. So some famous pairs are the variance and the mean pair, and also the pair of var and ES. So we call the variance is co-elicitable with the mean, and ES is co-elicitable with the var. So this is the foundation for us to achieve the backtesting approaches. Okay, so up to now, all the things are static, so we don't have the time flows. But what if we involve the time flows, the time changes? Then we have the backtesting comes into the play. So first, what is backtesting? Say we are the financial regulator, so assume that we are now financial regulators. And after each period, say it's 1 trading day, then we observe some new observations, like the log returns. Right? Here we plotted the log returns of Nasdaq index, or we can plot the log returns for some cash flows. Right? So this is the information that you observe. And at the same time, the risk forecast can be reported from the bank or financial institution. So here we have 4 different plots of the risk forecast provided by the bank. And but this may not be so clear. So we have 4 different colors representing 4 different forecasting methods. So you can assume that you have a time series, and you assume the underlying model to be normal, T, or screw T. But at the same time, you can also just provide the empirical forecast. All the methods are valid. But here, the problem is, so we want to ask which one is good, which one is bad. So which method is closer to the true values of the risk measures, which one is further, then actually this is not clear. This is non-trivial. And so our model is aiming to solve this question. And we further distinguish two scenarios. So by saying backtesting problems, we actually have two different cases. The first one, say you are the bank. Okay, so you come to me and I'm the regulator. You come to me with one risk measure, with one risk forecast in hand. In other words, just one line from here. You just have one forecasting method, and you provide me with the forecasting method, and you tell me that, oh, I'm actually not so sure whether this risk forecast is good or bad. Okay, so I'm going to tell you by designing some method, backtesting method, that whether this is good or bad. But the benchmark we're comparing with is the true value of the risk forecast. But actually, the true value of the risk measure is unknown. So what we only have is the one risk forecast with one forecasting method, and we're going to design some hypothesis testing method to tell whether this is good or bad. So in this case, this is called standard backtest or traditional backtest. But another scenario is the bank comes to you again. Okay, so with two forecasting methods in hand. So we have two lines in here and two different forecasting methods. The bank asks you, I'm not so sure which one is better. Okay, so you have two in hand, but you don't know which one is better. So in this case, you are comparing forecasting method 1 with forecasting method 2. But here, we don't have the true value as the benchmark. So you just compare different, the two data points that as the input. Okay. So in this case, this cannot be solved by standard backtest because standard backtest only have one input. Right? So this is another separate problem called comparative backtest. So we are going to solve two problems with two different methods separately for the two scenarios. Okay, so before we start solving the problem, we are going to first identify what problem we have in reality. So these are some problems that we have, some challenges. The first is that actually our data are not usually IID. Right? This is very, very natural to consider. So some previous work assume IID data for mathematical simplicity, but actually this is not reality. So in reality, the data are highly correlated. And then the second point is the predictions are even less clearly structured. So what it means that actually the risk forecaster can report the forecast arbitrarily. So they can decide which point that you want to forecast. Right? So you don't have a pattern. You don't have a fixed rule for reporting the forecast. Say we have some extreme examples like you are the bank manager, and today your favorite sports team just lose the game, right? And you're not happy, and say I just provide you with a bad forecast. And also you can even roll a die. You just randomly decide which one you want to report. These are extreme examples, but actually this is possible in reality. So in reality, the reports of the risk forecast are allowed to have no patterns. Okay. Finally, as a regulator, you usually don't know the true model used by the bank to produce the risk predictions. Or sometimes you even don't have an underlying model. The bank can just produce the risk predictions randomly or arbitrarily. Okay? So you don't usually know the underlying model. And it is also possible that the bank wants to report the true model, but due to some technical limitations, the bank may make some mistakes on their report. So a lot of complicated practical cases that we need to deal with in real life. So the ideal case is that why not we can just design a method that is model-free, independent on the distributions, independent on the dependent structure, also independent on the specific forms of the risk predictions reports, and also independent on the underlying model. Right, so this is our final goal. And here are some examples, and these data are actually simulated. So the real cases are even more complicated. So this is only for demonstration of the possible complicated cases that may happen in practice. Okay, so first, we have the so-called expanding business. So you are a firm and you are expanding your business, then more likely you have a linear trend of the loss observed and also the risk forecast reported. And this red line here is the ES forecast that is reported. Right, so you have a linear trend with the expanding business. And secondly, you have a trend, but you don't have a linear trend. But you do have a pattern. Okay? So here you have a sign trend of the loss and the risk forecast reported. And sometimes you can even don't have a pattern. Okay? So this is just RID data. And but at the same time, the firm have a poor forecasting quality. So it means here around the true value, you have some fluctuations because of some technical limitations. Right? So you have different complicated cases in reality. Again, in reality, this is even more complicated. So how you can deal with this case? And the problem is that you don't know the true value of ES. Right? So this is just the report. So by just observing the data you have, can you just say whether this red line is good or bad? This is non-trivial, right? So we are going to answer this question. And sometimes you can have multiple forecasts. You have multiple forecasting methods, and you want to compare among all the forecasting methods. So a lot of possible cases, a lot of challenges that we need to solve in practice. But after this talk, we are going to provide a solution of it. And here are some existing work. The first, one of the first papers on studying comparative backtest is a Note-Ziegel paper in 2017. And they studied both standard and comparative backtests for VAR, ES, and its backtests. But the problem is that they need to rely on the time series assumptions. So they need to have the parametric assumption, to have the dependence assumptions. And they also require the forecast to be provided to be also following the time series pattern. Right? So, and then we have some other bundle of papers studying the standard backtest on VAR and ES, but all of them are based on some parametric assumptions or dependence assumptions. Also, they rely on the forecast structure. What it means is that we need to have the requirements on the reported risk forecast. So they need to sometimes rely on the time series model, or they need to be produced by the linear regression models, and so on and so forth. So we have some requirements on the reported risk forecast. And the first model-free backtesting approach for standard backtest of ES is proposed by our paper with Rodu and Johanna. And this is model-free and doesn't rely on the forecast structure. But this is only for VAR and ES. And later, we have two other papers. The paper of Fan, Jiao, and Wang studied static tests. So the last two papers are actually not backtests, but they are testing the fixed parameter. So one single point forecast of the parameter. So this is called static tests, and this is studying the mean and variance case. But this is model-free, but we have requirements on the risk forecast provided because this is just one point forecast. Okay. And later we have a more general version. So the recent paper of Casgreen, Lasser, and Ziegel studied the static test for elicitable risk measures. So this is the large class of risk measures. And this is model-free, but just static, so just testing one single parameter. Okay. And for this paper, our goal is to design a standard and comparative backtesting approaches for the general class of elicitable risk measures, and this is model-free and doesn't rely on the assumption of forecast structures. So this is our final goal. And we want to achieve this goal by adopting the idea of e-values. Right? So, and we first start with the static test, and then move on to the dynamic case. Okay, so first, the notion of e-value. Actually, this is a brand new notion introduced basically as an alternative to the traditional p-values. And the term of e-value is proposed by the paper of Volk and Wang in their AOS paper. And they also studied the applications of e-values to the multiple hypothesis testing problems. And, but at the same time, the concept of e-values have been mentioned by other papers through some different names. Say the Schaefer's paper on game theoretic statistics, and also Greenwood et al. Studied a criterion of optimal growth rate for multiple testing problems. And e-values have been also adopted in some in different areas of statistics. So it becomes much more and more popular. And for example, Wang, Ramdas, and Ren and Barber studied the first discovery rate control problems using e-values. And also the paper of Volk and Wang studied the construction of confidence regions using e-values. All of these are traditional statistics, traditional statistics topics. And what is Smith Ramdas, what is Smith is here, and studied the multiple testing problem, but with the composite hypothesis. And also, very interestingly, e-values have been used in some other fields, like the Tierschip and the Greenwood paper studied the biomedical sciences for meta-analysis. And also, Hanzi and Ziegel studied how to use e-values to evaluate the probability forecast, say the weather forecast. And this is, sorry that this paper, this list of papers is not the most updated one. So up to now, we have a lot of new papers coming out for e-values, which I didn't have the chance to list here. But I just want to say that this topic has become more and more popular recently. Okay, so we talk a lot about the literature. So what is e-value? Again, this is proposed as the alternative to the traditional p-values. And here's the definition. Actually, the definition is not so complicated. This is quite simple. Right, so you have a set of hypotheses to test. And then you define the e variable as a non-negative random variable with expectation bounded by 1 for all the probability measures in the set Curly H. Right? So this is just a random variable with the moment bound for all the null hypotheses. And we simply call the realized values of the e variables to be e values. So actually, both e values and e variables are basically similar, basically the same thing. And e variable is, so if we change this inequality to equation and we have the robust version, so we have to take the soup here, then we call the e variable to be precise. So this is the definition. And later we can move this setup to a dynamic one. Right? So in a dynamic setup, we can define a very similar definition to be the E process, to be a non-negative process with the expectation bounded by 1 for all the stopping times. Right? So this is quite similar, but under a dynamic setup. Okay, so to understand this concept in an even simpler setup, so we can just take the set Curly H to be a singleton. And then, in other words, we have simple hypotheses. So under simple hypothesis, we have the E variable to be simply just a random variable, non-negative with the moment bound to be 1. And then we can, so we all know that one version of the definition of p-values is just a random variable whose expectation, whose probability below alpha is smaller than or equal to alpha for all the alpha between 0 and 1. Right? So, so 1 is the probability and 1 is the moment. And under simple hypothesis, e-values can usually be written as the likelihood ratios, so represented here. So likelihood ratio is one of the most popular or natural examples for e-values. Right? And then if we consider a Martingale, a super Martingale with the initial value smaller than or equal to 1, then actually this is the E process. Right? And you take the stopping time, any stopping time, you stop it, and then the stop Martingale is also an e-value. It's also an e-value. Right? So this can also be regarded as stopped Martingale. And it also appears in different literatures in different names. Say the betting score. So it is also called betting scores in the scenario of game theoretic statistics. And we all know that p-values are just defined as probability of a more extreme observation. So in other words, the p here represents probability, and the e here represents expectation. So that's why we call it e-value. But both of them are, of course, conditional on the data we have. And we all know that for p-test, we reject the null hypothesis when the p-value is small enough, smaller than some thresholds. This is the significance level. And correspondingly, for the e-test, we reject the null hypothesis when the e-value is large enough, right? Larger than the threshold, usually chosen to be 1 over alpha. So here you can see this is more like the reverse. So say if you have a e-value 10, then by definition you take inverse, you have the p-value 0.1. But this is only a demonstration. Actually, the e-value and p-value are, of course, not equivalent. And this is complicated. So the reason why we use e-values is mostly because e-values satisfy a lot of properties that p-values don't have. So these two are not simply equivalent. So these are the advantages, some of the typical advantages. So first, we all know that the construction of p-values is usually need to depend on stronger dependence assumptions. Say the ID assumption, or for example, we have listed before that for the existing ideas, existing models of backtesting approaches, based on p-values, we usually need to rely on the parametric or dependence assumptions. But for the construction of e-values, usually don't need to rely on strong dependence assumption. A simple example is that you have a bundle of e-values, and you want to combine them together. So one of the simplest ways is just take the arithmetic mean. Right? And then this method of combining the e-values is actually not dependent on any dependence assumption. So don't need to have any dependence assumption for the arithmetic mean of the combination method. And then, secondly, we all know that p-values are just CDF. So you need to calculate CDF, then you need to know the full distributional information of the test statistic. Then correspondingly, you may need some parametric assumptions, parametric models to calculate it. But for calculation of e-values, usually this is model-free. The reason behind is that you define e-values using moment bound. So you don't need to have the full distributional information in between. What you need to only know is the moment. Right? So usually the e-test is model-free. And then we have mentioned that the e-values can be regarded as the stop martingales. Right? Then by martingale property, by the optional stopping theorem, our e-test is usually valid at any stopping time. And as a result, it is valid for any finite sample size. So you can stop it at any point. But this is not the case for p-values. So for p-values, you have a sequential p-values. Usually you don't satisfy the optional stopping theorem. And then for p-value tests, usually you need to have the sample size to be large enough to have the asymptotic models, asymptotic validity. But for e-value tests, this is valid at any finite samples. And finally, the e-values are very easy to merge. So say you have sequential e-values over time. Say at day 1, you have E1, and day 2, you have E2. And all the way until t, you want to combine all the e-values together and find the most updated e-value. And one of the simplest ways is to just take the product. So you just multiply them together, and you have a new e-value. But this is not the case for p-values. So say you have two p-values, p1 and p2, and you take product. Actually, the new product is no longer a p-value. But I'm not saying that combining p-values is impossible. Of course, you have a lot of established approaches to combine p-values. But I'm only emphasizing here is, that the combination of p-value is usually more complicated than combining e-values. So all these advantages help us to achieve the model-free test, model-free backtesting approach that is independent on the dependence structure, independent on the model, also valid at any stopping time. So in other words, this is sequential test, and very easy to construct. So the E process is very easy to merge. Okay, so these are, up to now, these are the backgrounds for or motivations for us to achieve our method. And then we are ready to show some simple solutions. Okay, we are going to separately talk about standard tests and comparative tests. But we only start from static setups because this is the simplest one, and later we'll slowly move to the dynamic setups. Okay, so first, we solve the static case. For static standard tests, we have the following risk measures. So first, we have a regulatory risk measure, rho. So this is a single-dimensional risk measure, and we usually use it to determine the regulatory capital. So that's why it's called regulatory risk measure. But besides rho, you have another bundle of risk measures. This is multidimensional. That actually doesn't determine the regulatory capital, but they contain some useful statistical information of the underlying distribution. So this is called statistic. And combining rho and phi together, this is all the available information that we have. And again, we are not so sure about the real distributions of the financial data, so we are not sure about the true values of rho and phi. So what we can do is to have a financial institution, usually it's a bank, to report the forecast. But this is static setup, so here we don't have t, so just a 2-point forecast. The point forecast R is for the regulatory risk measure, and Z is for the statistic. And further, we define the statistic to be to have an identification function, which is given. This is an assumption of identifiability. Okay? And the bundle of risk measures of rho and phi is also has also identification function given as a small v and large v. Right? So this is a bundle of functions. So given this assumption and given all the information we have, we are going to test the following hypotheses. First, this is so we are testing the overestimation of the regulatory risk measure and the exact forecast of the statistic. So here, why we are interested in the overestimation or why we are interested in the underestimation of the regulatory risk measure. Because here, if we have underestimation, then we usually reject, right? So we care about underestimation because of the following. So say we are in the financial regulation practice, and say you have overestimation of the risk measure. Then it means that you have more financial reserves than expected, right? So to some financial regulators, this is not a severe problem because you are more conservative. And the financial regulators say, oh, this is still fine. You have enough financial reserves, you are just conservative, then this is fine. But let's say if we have the null hypothesis to be validated, then we have underestimation of the rho, then this is severe because you don't have enough financial reserves to offset your risk. Say if you have some extreme events like financial crisis, then you have significant consequences, like you can bankruptcy because you don't have enough reserves. So for financial regulation practice, sometimes you only care about you only care about underestimation. It is fine that you have the R to be larger than expected. So that's why we care about this one-sided test for regulatory risk measure. But at the same time, you can also think of a two-sided test for both the regulatory and the statistic. Then in this case, you care more about the underlying model. So if you have missed specification of the model, then usually you can reject. So for here, you only care about whether you have the correct model. But for the first one, you only care about whether you have enough financial reserves. So both hypotheses are dealing with totally different questions. Okay, so now we just show a very simple result. So of the E variable for the static standard test. So if we have some assumptions, then we have this very simple form. So you have the identification function plus 1 to be a precise E variable for the two-sided test. And recall that this V is only here. Okay, this is the nothing. This has nothing to do with the small v, just the large V. So the large V plus 1 is a precise E variable for the two-sided test. And further, if we have the function, the identification function is decreasing with A. It means that the less risk forecast you have, the more underestimation you have, then the more likely you want to reject. Okay? So if you have the monotonicity, then you further have the same random variable to be a precise E variable for the one-sided test. So same e-variable under monotonicity assumption is both the e-variable for the one-sided and two-sided test. And here the assumption is the so-called uniform boundedness condition. So within all the x and a and b, this identification function must be bounded by -1. And this is easy to satisfy in practice, not a very strong assumption. Okay, so this result is simple, and the problem is that it is only about test validity. So it means given the null hypothesis, we have the valid e-variables. So the given random variable is the valid e-variable. But here, this result has nothing to do with the power or the consistency. So to achieve the consistency, we have the following results. But we only solve the consistency with some special cases. So first special case is a single-dimensional case. So in other words, you just have one risk measure. You just have a regulatory risk measure without any statistic. In this case, you just write your risk measure to be a single-dimensional one, but this is the interval. And you assume this to be identifiable with strict this is identification function. So this is a typo. Strict identification function and uniformly bounded. Then under, so this is the same situation with this result, okay? But for a single-dimensional case, you have a much stronger result. So here, this is actually a characterization result. So it exhausts all the possible forms of e-variables for the null hypothesis of two-sided and one-sided tests. So this function, this function is a precise e-variable for both one-sided and two-sided tests, if and only if it takes the following form. So all the possible forms of e-variables are like this. This 1 plus a measurable function, which is in the negative, times the identification function. And in this case, you can also have a consistency. So when you have your null hypothesis of the one-sided test to be violated, in other words, you have underestimation of the risk measure, then you have the expectation of this function to be larger than 1. So it means you will reject the hypothesis in expectation. So this is sort of the consistency. And this is the building block of the following consistency results, which we will show later for dynamic setup. And the second case is a two-dimensional case. So when you don't have a single-dimensional risk measure, you have a pair. Then you need to rely on some other properties. You need to rely on the definition, the definition of Bayes pair. Actually, Bayes pair is defined in a very simple way, so very naturally. So when you have an elicitable risk measure to be the arc mean of the expected score, and you have also have a corresponding Bayes, you have a corresponding minimum, right? So this is minimizer, this is minimum. And if the phi here is the minimizer and rho is the corresponding minimum, this is called Bayes pair. So Bayes pair is the minimizer and minimum pair. So when you have the pair of risk measure is the Bayes pair, then you have the following result. Under the uniform boundedness condition, you have this form of random variable, 1 plus the measurable function times the difference of scoring function and the risk forecast, is a precise e-variable for the two-sided test. And at the same time, you have a weaker version of the consistency. That is, if you have the correct regulatory risk forecast, but you don't have the correct statistic. So this is the violation of the two-sided test. Under this case, you have the you can reject the null hypothesis in expectation. So this is for the two-sided test. And for one-sided test, you can have a much stronger result. So if you have this function is further decreasing in A, then the same e-variable is the precise e-variable for the one-sided test. But at the same time, you'll have a much stronger consistency result. So here, no matter what z you have, no matter what information you put into the statistic, as long as you have underestimation of the regulatory risk measure, you can always reject. So combining the two results, So if you have the underestimated regulatory risk measure, no matter what forecast you get for the statistic, you can always reject. But let's say you find a rejection and you verify that actually my risk measure, regulatory risk measure has no problem. Then what you can say? You can say that actually my model is misspecified. You have a wrong statistic. Right? Then you can also find a rejection. So this is basically the consistency. And here are some examples. So examples of e-variables for the common risk measures in practice. The first one is very simple. So just this ratio between the loss and the risk forecast is the e-variable for the one-sided test for the mean. And this is obtained through the identification function. Okay. And secondly, you can consider a pair of the mean and the variance and find a corresponding precise e-variable for both one-sided and two-sided tests. And this is this e-variable is obtained by the paper of Fan, Qiuqi and Wang. So this is our result include this one, this special case. And then we have the e-variable for the VAR, the one-sided test for the VAR, and similarly you can have the e-variable for the pair of ES and the VAR. This is obtained by our paper with Rodu and Johanna, and again, so this serves as a special case of our result. And finally, if, since we are considering the general class of elicitable risk measures, we can also have the e-variable for expectile, which is also elicitable. And but here, for the expectile and the mean, we restrict the space of random variables to be non-negative or bounded below. And we can also think of some other elicitable risk measures. So if you have identifiable risk measures, and you have identification function which is uniformly bounded, then we can find the corresponding e-variable for it. Okay, so these are about the standard test. Also, we talk about a separate problem of comparative tests. For comparative tests, we don't distinguish between the regulatory risk measure and the statistics. So what we have is only a multidimensional risk measure psi here. And for comparatives, you are competing between two different forecasting methods. So that's why the financial institution will provide two different forecasts, R and R star. Okay, and at the same time, we assume that the risk measure is elicitable with a given scoring function. Then we test the following two hypotheses. The first one is H minus. So this is very straightforward. So actually, the expected score for R, the focus R, is more than or equal to the expected score of R star. So in other words, R is better than R star by choosing the scoring function S. And similarly, you can also consider another way around, which is H plus. So say here, the expected score of R is larger than that of R star. So this is just switching the position of R and R star. Okay. So why we consider both? Why we consider both R, H minus and H plus? So imagine that we just have one of them, just have H minus, say. Then say you reject it. It means that you have sufficient evidence to reject this one, right? So so can you say that R is worse than R star? This is not so safe, right? Not so comfortable. So say for this one again, and you don't reject it, and you eventually don't reject it. Can you say that R is better than R star? This is not so comfortable, right? So but considering both, say you reject H minus, but you didn't reject H plus, then you are more comfortable to say that, okay, so R is worse than R star. And another way around, if you reject this H plus and didn't reject H minus, then you are comfortable enough to say that R is better than R star. So you combine the results for both tests, and then have a safer conclusion. Okay, so similarly, we can obtain the E variables for H minus and H plus for the comparative test. And again, you have a boundedness condition, and under the condition, you have the 1 plus H function times the difference between the two scoring functions to be a precise E variable for H minus. So under H minus, we can find this following random variable to be a valid E variable. So this is for validity, and it turns out that we also have the consistency. So if we have the null hypothesis to be violated, this is larger than 0, then similarly we can reject. We can reject the null hypothesis in expectation. So expected E variable is larger than 1. Okay, so this result seems simple, but actually we have some tricky things here. So you can look at this condition. Actually, this is not uniformly bounded. We only take the boundedness condition within all the x in a measurable set, curly K. So here, the R and R star are fixed. So why we do this is because, let's say, for example, here, this is for var, right? So here, this is the scoring function for var, and we take the difference between the two and plus 1. So if we consider the uniform boundedness condition, this is the boundedness condition over all R star and the L. So usually in practice, this difference is unbounded, and you have a very large bound. But so you may also ask, so why? So is it possible to say the R and R star and L are bounded, so bounded within minus M and M? This is okay, but this is too conservative, right? So you consider all the upper bounds and consider the special the worst case for all the parameters. Then usually you can have you need to have a very conservative bound. So given that the uniform boundedness condition is very hard to satisfy in practice, here we have a weaker version of the boundedness. So here, for a fixed R and R star, we only take the boundedness condition for all the x in a measurable set K, and to be bounded below by minus 1. And then we can have the valid E variables. So this is the small trick. This is different from the identification function. So for identification functions, usually the uniform boundedness condition is very easy to satisfy. But for comparative tests, this is a little bit tricky. So some technical details here. Okay, so up to now, these are only the static case, but we haven't touched the dynamic one, so haven't touched the backtest. So up to now, we just start talking about backtesting. For dynamic case, we have the new T here. So previously, we don't have the T. So when we have the T, the null hypothesis becomes this. So we have two null hypotheses. One is one-sided and another is two-sided, but we have the T here. And in this case, the forecast provided for rho and the phi are RT and ZT. And we need to pay attention that actually these two are random variables. Okay, so because we have the time flows, which are ft minus 1 measurable. Okay, so and for the hypothesis, the relation between the risk forecast and the true values of the risk measures are satisfied for all T. So this is the only difference. The first one is testing the underestimation of rho, and second one is testing the misspecification of the statistic. So we have different focus on the two null hypotheses. Okay, so then we go back to our previous question. How we can do the backtest? How we can tell whether the forecast is good or bad? Then the answer is that you just follow the steps. First, you have the bank will announce the risk forecast, and this is the information that you first received. For rho, we have the RT, and for phi, we have the ZT. And don't forget, we are the financial regulator, so our first job is to determine a so-called predictable batting process. So this is a process which is predictable, ft-1 measurable, and take values between 0 and 1. So this lambda t is actually our private information, so you don't need to show this to the bank. And then you observe the realized loss. The realized loss comes in. So for all the information you have, you just plug them into the identification function we have before, and you construct the e variable, which we have constructed for the static case. And so here you construct a single e variable for time t. And as t goes, then you have a bundle of risk measure of e variables, right? And then you have lambda t, you have et, and then you combine them together to get this following e process. So this process is actually very simple in terms of its form. So it's just a product of all the mixtures between 1 and the e variable we have here. And the weighting function is the batting process. So it's just take the mixture and then take the product. So why we choose this form? Why we choose this form of merging? One of the reasons is that actually this is the best we can do. This is proved in the recent paper of Qiuqi and Wang that this way of merging the e variable is dominating other sequential e merging functions. Right? So this is the best we can do. And another advantage of this kind of mixture is that after doing this product form, we can achieve a supermarnico. So this M here is a supermarnico. And by Marnico properties, you can have the well-known Wills inequality. And so say if here we choose the rejection threshold to be 1 over alpha, we reject the hypothesis when the e process exceeds this threshold. Okay? And if we choose the threshold to be 1 over alpha, then we can control our type 1 error to be within alpha. So this is type 1 error control, but with the soup here. So with the soup here, we mean that our test is anytime valid. So it's satisfying the, yes? Yes, you're right. Thank you. Yeah, so here we take the t, but this can be finite or infinite. Okay. Okay, so since we have the superior here, then we can have the optional stopping property, and our test is valid at any stopping time. As a result, our tests do not rely on the fixed sample size, so we can stop at any time. So we don't have a fixed sample size. And also at the same time, we don't rely on asymptotic models, because we can stop at this sequential test, and at any time point, our test is valid. So we don't need to rely on asymptotic models. The test is non-asymptotic. And finally, our test is totally model-free, so you don't need to rely on the underlying distributions, dependent structure, or anything. So what we only have is, what we only need is the forecast and the loss. Right? So that's the only information that we need. Okay, this is about standard test. And for comparative test, we have, this is a different problem, but we can achieve the comparative test using some similar logic. So we consider two different hypotheses. We have mentioned this before, H minus and H plus, but with the time flow t. But here, the dominance here have the condition, the conditional on ft minus 1. So this hypothesis means that the RT forecast conditionally dominates R star t. And again, RT and R star are random variables. And later we will say that actually this null hypothesis is quite strong. Right? But later we will provide some alternative, some solutions for it. But first, I want to say that actually this one is quite strong because this requires the domination of R over R star for all the time t. Right? So this is quite strong. Okay, so to achieve the comparative backtest, we have the similar procedures. So first, you also observe the competing forecasts for R and R star, and then you determine the batting process, and you observe the loss, and you plug all the information into the E variable we get before for the static case, and then you construct the E process using the similar way. But this is only for M minus. This is only for H minus. So to test H plus, you need to calculate another E process, which is M plus, but you just switch the positions of R and R star. So quite easy to obtain. So you calculate M minus and M plus separately. Okay, so here's the trick. Because you need to have the two null hypotheses testing at the same time, you have different scenarios. So that is the so-called three-zone approach, and this is actually adopted by comparative backtest. This is established, but we have some slight modifications. Okay, so this is like traffic light. Okay, so the first case is that for both hypotheses, you reject the first one, but don't reject the second one. So you reject H minus, don't reject H plus. So what it means is that you reject here at here, but this one gets passed. So what it means is that R is worse than R star. So it doesn't pass the comparative test. That is why we have the red region. So this is for R, right? So this is bad for R. And similarly, if you reject H plus but do not reject H minus, then you are in the green region. It means that R is better than R star. So you make conclusions by combining the results of H minus and H plus. But the problem here is that it is also possible that you are in the yellow region. That is, you reject both. So say, again, these two null hypotheses are strong, right? So it is possible that actually you can reject both. Say you have one example that say at point 1, 2, and 3, R is better than R star, but for 4, 5, and 6, then R star becomes better than R. So this is possible, and this is highly possible in practice, because when the bank is not so sure about which forecast is good and which forecast is bad, usually they are quite close, right? So you don't have the very strict dominance over all T. So this is possible that both of the null hypotheses are rejected. So when they are both rejected, we are in the yellow region. And for p-test, if we do the same thing for p-test, if you are in the yellow region, you cannot tell anything. So you just tell the bank, oh, I'm not so sure which one is good. Okay, so you just go back and do further investigations. And this is the only answer that you can provide. But for e-test, we believe that we can have more valuable information, although we are in the yellow region. So that is the following. So we're doing the following. So because we are doing the sequential testing, so we have the two E processes together, then we can compare the two E processes of M minus and M plus. So first we can compare their magnitude, right? So say we have the two processes, and we take the final time point. So it is like their average scores, right? So the average scores of H minus and H plus. So if the score of H minus is lower than H plus, then it means that R weakly dominates R star by magnitude. So this is our definition. Okay? So we define this to be weakly dominating R star by magnitude. So this is comparing the final scores. And again, we can also compare the speed of the two E processes and see which one reaches the threshold first. Right? So if M minus is slower than M plus, so we compare the stopping times of both. If M minus is slower than M plus, it means that R weakly dominates R star. So this, although we can reject both, so we cannot tell anything of the strict dominance, but here we can compare the two E processes and find some useful information. This is a little bit abstract. So here is one example, and this is from our later numerical studies. So here we have two competing models or forecasting methods, and you want to see which one is better. Okay? And actually, we find that this is in the yellow region. So both of the E processes reaches the threshold, and we reject both. But although they are in the yellow region, here you can see a very obvious dominance of the M plus over M minus, right? So here, and we also calculate their differences, and this is always larger than 0. So when we calculate, when we compare the magnitudes of both, one is strictly larger than another, and when we calculate the speed, then one is faster than another. So by these observations, we're actually comfortable to say that m minus is always below m plus, then the weak dominance of the minus 20 over plus 20 is clear, right? So this is, although we can reject both, we are in the yellow region, but here we can tell some useful information by comparing the two E processes. Okay, and finally, we also have another awkward situation. So it is also possible that you reject neither of them. Okay? So you don't reject H minus and H plus. And in this case, you cannot say anything. So you just tell the bank, I'm not so sure. So, you need to do further investigations. But here, I want to emphasize that this case is very likely happening in practice. The reason behind it is the following consistency result. So we obtain a consistency result under a simple setup, which is IID. So when we have assumed the E variables are IID, then we have the following consistency. But before this, I want to say that our test is always valid for any betting process we choose. So no matter how bad it is, so we can arbitrarily choose the betting process. This can be always constant, or we can choose it cleverly by some optimization algorithms. But no matter what lambda we choose, our test is always valid, as long as it is between 0 and 1. Right? But what is the cleverest way of choosing the lambda? So if you choose lambda cleverly, then you can achieve better power. Right? Then, so what is the best way of choosing the lambda? Theoretically, if you know the distribution of all the E variables, then you just calculate their expected growth rate, log growth rate. Right? So this is the growth rate of the E process. And if you choose the lambda that maximize the log growth rate of the lambda of the E process, then this lambda is the best, theoretically. But this is quite ideal because in practice you don't know the distribution. Right? So this is only a theoretical benchmark. So how you can choose the lambda cleverly or in a proper way? This is what we define. So if you choose the betting process, then which is asymptotically equivalent to the best one. Right? So the asymptotic growth rate for both are actually the same. Then we say the lambda is properly chosen. So under a properly chosen lambda, we can achieve the power of our test to be asymptotically 1. Right? And if we have the null hypothesis to be validated. This is the power. So if we can choose the lambda in a clever way, then we can achieve the power close to 1. Okay, so you may wonder that, is it difficult to choose the proper lambda? The answer is not, because we have some established method in the literature of choosing the lambda in a clever way, which satisfy this property. So under some nice assumptions. So this is not so difficult, but for this paper, we are not focusing on this. So we are not proposing new methods of choosing lambda. So, but I'm just saying that we have some established methods on this, and no worries on this. So this is about the consistency. So go back to here. Why this is related to the last point? Because again, these two null hypotheses are strong. So we must have at least one of them to be validated, right? So we cannot have both of them satisfied. So if one of them is validated, and then we choose the lambda t cleverly in a proper way, then we can reject it for sure, as long as we have the sample size to be large enough. So this case is seldomly happening in practice. But what if we just encounter it? We can either say you cannot have the enough evidence to have the dominance, or you just go back to the bank and say you need to provide more data. Yes. Okay. So these are about theoretical framework. And finally, I want to say that this project is mainly focusing on the it's aiming for practical applications. So actually, simulation and numerical studies are very important for this project, but this is still ongoing. So we only have some preliminary results up to now, and but this helps us to have a better understanding of the theoretical framework. Okay, so up to now, this is still toy model, but I hope it at least prove that our method makes sense. And so the loss is simulated to be IID with the standard normal distribution and with the linear trend. So this is an artificially added linear trend. And we repeat the simulation 1,000 times and see the performance, see the average performance. And for the forecast, we provide 5 different methods. The first method is, so say you know the true value, okay? You know the true value of the risk measure. And secondly, you can deliberately underestimate your risk measure by 10% or 20%. Right? So this is depending on the bank. So you can report it arbitrarily depending on whether you are conservative or not. And then you can also overestimate your forecast by 10 or 20%. So in total, you have 5. You have 5 different forecasting methods. And we are comparing among all the 5 methods. And the rejection threshold is, the lowest rejection threshold is 2. Right? So if it, finally it doesn't reach the 2, we then say we don't reject it. And here is this beautiful figure, and this for var, and we choose the scoring function like here, and this is the result. So we compare all these five methods among each other, and intuitively, it is very easy to say that the plus 10 is better than plus 20, right? So they are both overestimating. They're both not perfect, but plus 10 should be better than plus 20. So let's see whether we get the intuitive result. So when you compare, so when you regard the R as the plus 10 and R star as the plus 20, and you test the H minus, then you have a very small e-value. It means that you don't reject it. Right? But at the same time, you switch the positions of the plus 10 and plus 20, and you consider the H plus, right? Then you reject H plus. So you reject H plus, this is the red region, and doesn't reject the H minus. So in this case, you're safe to say that actually 10 is better than 20. Right? This is intuitive. And we have a lot of very similar results. And here, the interesting thing is the orange and the dark red are actually both red regions. But here, so the larger the e-value, the darker the color. So this also cannot be achieved by p-values. So we can have the stronger evidence when we have the e-value to be larger. Right? So you have different colors in the red regions. Okay, so you have all the intuitive results to be satisfied, and for those in the yellow regions, these are just say you compare between minus 20 and plus 20, you have a rejection, but you have you test the H plus, you also have a rejection, so you are in the yellow region. Okay, so for those in the yellow region, we can also tell something. This is from our previous slide, right? So you test, you compare between minus 20 and plus 20. This is very difficult to say intuitively which one is better, right? But here you can have a very clear evidence that the M plus is always above M minus, and you can also calculate their difference and plot it here. So minus 20 weakly dominates plus 20 by magnitude because you have the final scores, and it also weakly dominates plus 20 by speed because you also can compare between the storming times. Right? And you have some similar results for ES. This were another scoring function for ES, and you also have all the intuitive ideas to be satisfied. So plus 10 is better than plus 20, and minus 10 is better than minus 20, and so on and so forth. And you can also compare between minus 20 and plus 20. You can still find the clear weak dominance. And I think this is quite interesting because you can regard the two M minus and M plus as two like the athletes. They are racing each other. And you want to compare their average final scores, and also you want to compare their speed. Right? And, or you can think of the two as two traders, and they're trading the stocks. And they're competing each other to try their best to achieve the highest E process. But after they do this, you can see different performance. Right? So you can compare between, always compare between the E processes and to find the weak dominance. Okay, so this is for for subsequent work. This again the ongoing project, and we are doing some further numerical studies on some more realistic data. So now this is still toy model. So we can try the time series data or the real data with Nasdaq index, and also try some real estimation methods like the full parametric methods, semi-parametric methods, and so on and so forth, and competing each other and compare the final scores. And also for theoretical framework, we can also study the expectiles because the backtesting method for model-free backtesting methods for expectile is still blank in the literature. So there are something to do. Especially there's some characterization results like what is all the possible forms of E variables for expectiles, and so on and so forth. So you have a lot of space to study in the future. And again, this is one of my independent projects, first independent projects, and studied now, this for myself for now, so still not so mature, and your suggestions and comments will be welcomed. Thank you.
Thank you very much for this very interesting talk. Any questions?
Yes.
Thanks. That was a great talk. Okay, so I had maybe a suggestion of just, and stop me if you've already looked into this or something. But when I see this problem of wanting to compare two different scores, like in this comparative setting, and you're framing it essentially as like a sequential testing problem. If I were a bandit person, I would look at this and think of it as best arm identification. And right, because essentially you have like two arms and you'd like to pick like which one is better, and in the best arm identification literature, it's all about trying to do this as quick as possible with some like amount of confidence. But then there's also other questions of things like, suppose you have K arms, or maybe like uncountably many arms or something like that. So to translate that into this setting, it would be like if you have maybe a huge collection of I guess scores or things to compare from, or to compare to. I'm just curious, do you think that would be like an interesting thing to look at, or have people looked at things like where you don't just have maybe two things that you're comparing, but actually maybe a large collection, potentially uncountably or countably infinite or something like that?
Oh, thank you so much. I think this is a very valuable, interesting suggestion. So up to now, because the framework of node and Ziegler is also studying the comparing between two of the different forecasting methods. So it would be very valuable if we can compare like multiple risk forecasts together. But now, to be honest, I'm not so sure of how we can do it. So maybe we can consider the multi-dimensional E processes, or because this is quite interesting. But no, to be honest, I don't have very clear idea of how we can do this. But again, this is clearly a potential future direction for it. Thank you.
Other questions?
Yes.
Hi, thanks for the talk. My question is regarding that betting process, the lambda t. You said there were all kinds of methods to select that lambda t. Yep. Can you give us some intuition on, are you selecting the lambda t to have good asymptotic properties of the test? Or is it somehow related? Is it a data-driven kind of selection, or?
Oh, okay. Thank you so much. So actually, because here we actually start from this theoretical, just ideal case. So this one is theoretically the benchmark that we think is the best. But the problem is that usually we don't know the true distribution. So what we usually do is to resort to some empirical methods. So let's take the Q to be empirical probability measure and calculate the empirical mean. And then we find the argmax of the empirical mean of this. So usually this is the logic that we do. But yeah, but this is not ideal because the ideal case is that you know the Q. But if you don't know the Q, you just calculate empirical mean. And then you find the argmax. And
that e process has nothing to do with the data itself. It's just to get the right dynamics. That e process has nothing to do with the data, right? You're just saying that's non-negative random variables from an alternative.
Actually, the e processes are constructed from the data. So it is actually here. So you can plug in the data you have and into the function that we defined before, and then you construct you merge all the e variables together. So,
okay, so you have an e of t, and then you have that, and then you'll go empirically to solve for lambda.
Yes, yes.
Oh, okay,
yes.
okay.
Thank you.
Other questions? Didn't he answer them previously?
Actually, this is the first time I saw this work, so I got quite curious. So what if I just plot all the processes for each of the forecaster, and now I have many processes, and just pick one of the best? That seemed to be intuitively a good choice. So have you thought about that, or is there something wrong with that idea?
You mean
for forecasters, I just draw one e process for each of them. I pick the one that has the highest e value in the end?
You mean so what? To me, like we do a standard backtest for all of these and then compare. I don't know if it is making. Yeah, I need to check. So if this makes sense, maybe it's easier way compared to the comparative test. But
well, of course, the e process that is biggest is the worst, right? That is the one that you get the biggest evidence against. Mm-hmm. So the e process that is low should be better, but of course that depends on the lambda. So there's some complication, but it seems to be intuitive to think that way at least.
Yeah, this seems intuitively making sense, but we need to have the theoretical, like so if one of the e process is larger than another, so what it exactly implies, so theoretically. So we need to have a theoretical foundation of it. But yeah, I think this makes sense intuitively. We can try this.
Thank you, Rodu. Any other question?
Yes.
Hi, thank you very much for the talk. I'm just wondering if there's any intuition behind why we should prefer the minus 20% estimation over the plus 20%. Why would one choice be better than the other?
Oh, okay. Thank you. So so maybe it's like this. So when you compare between the two different methods, you actually so you have method 1 and method 2, and you want to see which one is better. After you find a solution, actually it is usually so the better one is closer to the true value. So say the true value is in the middle, and you underestimate it by 10%, and then underestimate it by 20%. So 20% is lower than the 10%. So it's further from the true value. Yeah.
Minus 20 and plus 20.
Yes. So your true process would be in between the two, right?
Oh, okay.
So why does it prefer the minus 1? You're saying here
oh, okay.
instead of the plus 1, even though in some way I would understand that to be an equivalent bad choice.
Yeah. So first, I think for this case, we are comparing between the two e processes because it is hard to tell intuitively which one is good and which one is bad. So, but after we find a solution, it is highly possible that actually the minus 20% is closer to the true. So, or the loss or the expected loss for this method is better than this by the plus 20. So I think the reason behind so why we are doing this is it's very hard to tell intuitively which one is good, which one is bad. So after we find a solution, we can only say that the expected score. So when we calculate the expected score for both, the expected loss for this one is lower. But we cannot say, okay, so magnitudely, so which one is further, which one is closer. So for this one, it's very hard to tell. And for the practical cases, we have some much more complicated estimation methods. Like we can choose the full parametric method or the semi-parametric method, or we use some EVT methods. So a lot of different methods, and for these methods, it is even harder to tell intuitively which one is good, which one is bad. So that's why we are doing, I think that is why we are doing this kind of thing, and to calculate the expected scores. But yeah, you're right. This is very hard to tell very intuitively, right? Yes, thank you.
Yes.
Qiuqi, thank you for your talk, and I want to ask you a very intuitive question. Like, suppose you have two risk measures, and you can consider their linear combinations or say convex combinations. So, well, there's a if I plot another e-process based on these new measures, well, this e-process just like between the upper one and the lower one. Yeah, there's a third measure. I do this with the first risk measure or the second risk measure. There will be 6 lines, right? So well, the 4 lines when I compare the convex combination of these new risk measures, will stay in the upper bound of your blue and red curve?
I think this also depends on your forecast, right? So your forecast also need to be mixtures.
Yeah, the forecast will be the same. It's like I assume that the statistics is accurately accurate, and I just want to test whether it's overestimated.
I think this is not necessarily, because for again, so if you think about the combination of 2 risk measures, you need to at least find the identification function, right? So identification function is not a mixture. So yeah, so if you have this kind of complicated case, first you need to guarantee that this is identifiable, right? So say you take the mixture between bar and ES, and this is, yeah, you need to find a new identification function for it, right? And of course, this is not identifiable. Yeah. So this is complicated. So I think it's not necessarily that the E process is just in between. So it's case by case. But also it depends on why you are interested in this kind of question.
I want to know whether there's a dominance relationship.
Mm-hmm. Yeah, I think it's not necessarily. So yeah, complicated question.
Well, the great thing is that you'll be able to discuss this over coffee. Let's join me in thanking our winner again for a great